Alright, now that I've confused the hell out of you about ground, let's continue to explore the features of this power supply. The Tektronix CPS250 triple output power supply additionally features two adjustable power supplies, A and B, each capable of producing adjustable 0 to 20 volt output. What's nice about these two sources is that they are independently adjustable and isolated from one another and from ground. Importantly, to take advantage of the independent nature of these two adjustable sources, one must ensure that they remain independent by placing the selector switch in the upper right-hand corner to independent mode. The selector switch also allows the user the options of placing the sources in series with one another or in parallel with one another. We'll explore these options in later lectures on series and parallel DC circuits. For now, let's keep the A and B sources in independent mode. Closer inspection of the A and B output terminal pairs lets the user know that the adjustable sources each have an upper limit of 0.5 amps or 500 milliamperes. Given power as the product of voltage and current, a max of 20 volts times a max of 500 milliamperes demonstrates these two sources also have an upper limit of 10 watts of power each. Changing the voltage output of the adjustable A and B sources is done via the corresponding voltage adjustment knob. The power supply layout makes use of a simple color scheme to identify which knobs control which outputs. You'll note the A source is identified by a gray box. The voltage and current control knobs in the gray box control the gray A source. Here, the A voltage knob is turned a little past halfway. We might expect an output of more than 10 volts, but less than 15 volts. The A current knob is pegged all the way clockwise. This means source A will provide up to the maximum of 500 milliamperes. We'll explore current limitation in a moment. Similarly, you'll note that the source B is identified by a blue box. The voltage and current control knobs in the blue box control the blue B source. It looks like the B voltage knob is turned a little less than halfway. We might expect an output of more than 5 volts, but less than 10 volts. It looks like the B current control knob is also pegged all the way clockwise. This means source B will provide up to the maximum of 500 milliamperes. Again, we'll explore current limitation in a moment. The needle meter on the left displays voltage, whereas the needle meter on the right displays current. The selector switch between the two needle meters can be toggled between the gray A source and the blue B source. Right now, the power supply is set to display the output of source A. When I turn on the power supply, it looks like the voltmeter needle jumps to maybe 12.5-ish volts, midway between 10 and 15 volts. You note the ammeter needle indicates that source A is not providing any current. This is to be expected since no closed electrical circuit exists. How accurate is this needle voltmeter? Not bad, but it's not terribly precise either. At most, the analog scale is used to approximate the output. More accurate voltage measurements can be made with a Dmm and Dc Voltmeter mode. A DC voltmeter demonstrates that source A is actually closer to 13-ish volts. A minor turn on the gray voltage control knob can dial the source A down to 12 volts. When I toggle the selector switch to source B, the voltmeter indicates source B is maybe 5-ish volts. Similarly, you'll note that the ammeter indicates that source B is not providing any current. This is also to be expected since no electrical circuit exists. A DC voltmeter demonstrates that source B is actually closer to 6 volts. A couple turns in the blue voltage knob cranks source B up to a maximum of 20 volts. When we toggle the selector switch back to source A and measure source A's output with the voltmeter demonstrates that source A has remained reasonably close to our previously adjusted value of 12 volts. In short, source A and source B are two independent and independently adjustable sources. Let's make use of the adjustable sources to provide current to a load resistor. Consider source A currently set at 12 volts, forming a closed electrical circuit consisting of a 100 ohm resistor. An application of Ohm's law demonstrates we should expect 120 milliamperes of current. A subsequent application of the power equation demonstrates the resistor will consume 1.44 watts of power. If we were to use a pretty beefy resistor capable of handling 2 watts, we should be just fine. When we build the circuit and turn on the power supply, the analog current scale demonstrates source A seems to be supplying an amount of current reasonably close to our theoretical calculations of 120 milliamperes. You'll again note that the analog ammeter scale isn't terribly precise. We'll explore the DC ammeter function of the DMM in an upcoming lecture that makes possible more accurate measurements of current. Let's do the same with source B, currently set to 20 volts, also forming a closed electrical circuit consisting of a 100 ohm resistor capable of handling up to 2 watts of power. An application of Ohm's law demonstrates that we should expect 200 milliamperes of current. A subsequent application of the power equation demonstrates the resistor will consume 4 watts of power. You'll note that we'll be overloading this particular resistor by twice its rated power of 2 watts. It should handle it, but not for long. We might expect this resistor to heat up and smoke a bit. This should be fun. When we build the circuit and turn on the power supply, the analog current scale demonstrates source B seems to be supplying an amount of current reasonably close to our theoretical calculations of 200 milliamperes of current. The observant among you will note wisps of smoke curling off this resistor, and the pane is rather quickly turning an ugly shade of brown. A thermal imaging camera really tells the truth of how far beyond the power rating we're pushing this particular resistor. Burning electrical components makes a great segue into a discussion on current limitation. This is a current-limited power supply, meaning there are hard upper limits of current and power this power supply is capable of delivering, beyond which output will be attenuated or reduced to prevent damage or disaster. This is a great feature for a basic electronics lab where what can go wrong often does on a disturbingly regular basis. You'll note each adjustable voltage source can provide an upper limit of 500 milliamperes of current. This upper current limit is adjustable via the current control knobs for each source. With the current control knobs all the way clockwise, each source could provide the maximum of 500 milliamperes. Halfway, we might expect a maximum of 250 milliamperes. 1/4 turn clockwise, we might expect 125 milliamperes, and so on. As previously, consider source A, currently set at 12 volts, that would ordinarily supply 120 milliamperes of current to a 100 ohm resistor. If we wanted to, we could set an upper limit of 125 milliamperes for this A source by keeping the voltage control knob at 12 volts and dialing the current control knob back to a 1/4 turn clockwise. When we turn on the power supply, everything behaves as we might expect, where 120 milliamperes of current flows through the 100 ohm resistor when it experiences a 12 volt differential. Given 120 milliamperes is below the user adjustable limit of 125 milliamperes, source A provides all 12 volts and all 120 milliamperes of current without a hint of complaint. The user adjusted current limit, however, establishes a hard limit of 125 milliamperes in the event of a mistaken connection or a short circuit. For example, consider a 0 ohm short around the 100 ohm resistor. The 0 ohm short would present no opposition to current flow, and if the source wasn't current limited, theoretically infinite amounts of current would flow through the short. Always a bad idea. However, given we dialed source A's maximum current down to 1/4 of 500 milliamperes, we should expect at maximum roughly 1/4 of 500 milliamperes or 125 milliamperes of current to flow. Allow me to demonstrate. The moment the short circuit is established, current spikes to roughly 125 milliamperes and ceases to increase. Importantly, 2 events simultaneously occur. 1. The overload indicator on source A illuminates, indicating source A is presently hitting the user adjustable upper limit, in this case 125 milliamperes. If this light turns on, either your current setting is too low or something stupid like a short circuit is happening. Short circuits across the terminals of a source present no opposition to current flow and are generally to be avoided at all costs. 2. The current limited power supply recognizes something stupid is happening, in addition to throwing a red flag on the play, takes active steps to avoid a total disaster by reducing voltage. You'll note the voltage necessary to push a maximum of 125 milliamperes of current through an incredibly low resistance short is not our previously established setting of 12 volts, but rather a much, much smaller, essentially 0 volt differential. As soon as we remove the 0 ohm short around the 100 ohm resistor, source A immediately bounces back up to the desired 12 volts and steadily supplies the required 120 milliamperes of current as if nothing unusual has happened, all thanks to the current limitation feature of this power supply. We can use the current limitation feature of the power supply to make sure components don't go up in smoke. Consider a 100 ohm resistor intended for power applications of less than 2 watts. What if we kept source B at 20 volts? However, current limited it to 1/4 of 500 milliamperes or 125 milliamperes by backing the current adjustment knob off to 1/4 turn clockwise. How much power would a 100 ohm resistor dissipate if it was limited to a max of roughly 125 milliamperes of current. An algebraic permutation of the power equation demonstrates that power equals current squared times resistance. Substituting in the upper limit of 125 milliamperes and the resistance value demonstrates that this resistor will dissipate at max roughly 1.6 watts of power. In this occasion, we'll be well under the power rating for this particular 2-watt resistor. Importantly, what magnitude of voltage should push 125 milliamperes of current through a 100 ohm resistor? An application of Ohm's law demonstrates 125 milliamperes flowing through a 100 ohm resistor necessitates only a 12.5 volt differential. Consider source B, currently set at a maximum of 20 volts and a maximum of 500 milliamperes. This is way more than we need on both accounts. If we kept source B's magnitude at the 20 volt maximum, yet dialed the maximum current down to 125 milliamperes, we should anticipate some predictable behavior given this power supply is current limited. Namely, we should observe voltage, currently set at 20 volts, to drop down to only 12.5 volts, such the maximum permissible amount of 125 milliamperes of current flows through the 100 ohm resistor. And additionally, beyond actively controlling the output voltage, we should see the power supply throw a red flag in the play and indicate that it's in an overload condition by illuminating the overload LED for source B. Let's see if this is the case. As we anticipated, voltage drops from 20 volts to roughly 12.5 volts as current pegs the user-adjustable upper permissible limit of 125 milliamperes. The overload light illuminates, indicating we're pegging the limit. Importantly, given the current limited nature of the power supply, the resistor doesn't go up into smoke this time. Oftentimes, the current limitation feature is used in this fashion to prevent current from exceeding some user-predetermined maximum beyond which may damage the components under inspection. The current limited power supply actively reduces output voltage such that current does not exceed this user-adjustable maximum. Alright, this is really as far as we can get without introducing the ammeter. We should probably wrap it up. We'll make use of DC power supplies in later lectures. In conclusion, this lecture took a look at a basic DC power supply. We examined operation of a DC power supply and discussed the referencing aspect of a ground connection. Additionally, we discussed the current limitation feature of a current-limited DC power supply. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.